Previously, when we were looking at average rate of change, we drew secant lines, right? And we use secant lines to maybe approximate the function within a certain interval or within the bounds of the endpoints of the secant line, right? Or the bounds of the average rate of change interval. And so now I'm curious, what if we shrunk that interval? Okay, and so let's explore this with Desmos. Okay, here's an example that I have. Okay, so you can see in red is the function that's shown, okay, on a specific domain, that's fine. And then I have points P and Q labeled. What I'm going to do is shrink the interval by fixing P. So as the animation goes through here, P is not going to move, Q is going to move closer to P, right, so that the interval shrinks. And what I want you to do is look at the average rate of change calculation, which I have here in the second line. So f of 1 minus f of a over 1 minus a. So right now it's saying that the average rate of change is minus 1. And what I'm going to do is move a, okay? So I want you to look at what happens to the average rate of change first, just to see what happens. Okay, so here we go. I'm going to move a. And so then we get average rate of change is 0 at when x is 3, and then moving, it goes more positive, 1, and then it's continuing to increase, and then, oops. And so when a is equal to 1, the line disappears, right? Our secant line disappears. Why is that? Well, because a is 1, right? And I'm dividing by 0, so that means bad things happen. So that can't happen, right? So, okay, can happen, but when we're really, really close, I'm wondering, like, if I were to make a line now, right? For a line, I need a point, I need a slope, right? Um, I want to make a line that intersects the function just at point P, well, and Q at this point. What would that slope be? We have the point, right? So what would you estimate the slope exactly at P to be? Okay, again, I'll bring it in and again, the average rate of change was the slope of the secant line. Maybe we can use that to see what the slope of this new line would be. 1, 1.2, 1.3, 1.6, now 1.7, 1.8, 1.9. It's getting closer to 2. And in fact, if we hide the secant line and instead look at this other line that I put in purple, it's pretty close to blue, but you can look at the equation and see, oh, that has a slope of 2, right? And that would intersect the function, the red function here, exactly at P and only once. When that happens, the secant line becomes instead what we call a tangent line, and the slope of that tangent line is no longer the average rate of change, it's called the instantaneous rate of change, so IROC. And yes, I know IROC, you rock too, but I can't put that, there's no acronym in mathematics for you rock, so IROC instead. So F, we have P and Q, okay, here's the technical definition. To get the slope of the tangent line, right, the instantaneous rate of change, we have to do the difference in y's over difference in x's, and then there's this lim notation. All it's saying is bring x2 closer to x1. So that's, again, fix P, bring P closer, or bring Q closer to P, right? And then we get a slope, or we can just estimate it, and we can construct the tangent line just by using point and slope, okay? So, yep, that limit notation, that's literally the first thing you see in calculus. So more on that when you take that class. But now the idea is, how can we use the notion of tangent lines to tell where the instantaneous rate of change is positive, negative, and 0? So also just a comment, the textbook, when you're using it, in whatever platform we use, instantaneous is sometimes left out and it just says rate of change. So if it doesn't say average, assume it's instantaneous, okay? But what we want to do is see if we can identify where the rate of change is positive, negative, and 0 on this graph. And so we have to use this idea of instantaneous rate of change is the slope of our tangent line. So when we look at the graph of the function, here we are, okay? Can we estimate where the instantaneous rate of change, where that tangent line this slope of the tangent line, right, is positive, negative, and 0? I think we sure can. So with the tangent line, I need to just kind of pick a point, right? So I'm going to pick a point and then imagine constructing a tangent line. So a line that intersects the function once locally, right? Locally. So there, does that line have positive slope, negative slope, or 0 slope? It's positive slope, right? So I'm going to say that in this region, at least right here, this was a representative point, but all in this region here, so from maybe here on, right, I'm going to say the instantaneous rate of change, is positive because the slope of the tangent line would be positive. Same sort of thing would happen over here. Again, pick a point and we get a tangent line that has positive slope, and that would happen all the way till about here. Okay, so again, I rock is positive there. Okay, so we have, yep, and this got erased. We'll add it back in. I rock greater than 0. Okay, and then in between, I'll change this to blue. In between, again, take a point, look at the tangent line. Okay, the tangent line has negative slope, so in between here, I would say that the instantaneous rate of change, okay, which is the slope of the tangent line, is negative. Okay, and the only other thing is we have to identify where it is 0. That would be exactly at the peaks and valleys, also known as extreme values, which we will see later on. But those are where the instantaneous rate of change is 0, precisely at those places. Okay, so when you're thinking of looking for instantaneous rate of change based on a graph, look at where the slope of the tangent line is positive, negative, and 0. Okay, and so one example that we could do here is with the tangent line, if we just needed to do something with it, right? We could say, okay, we want to find the rate of change. And again, they omitted the I, so put an I there for us. And so we want to find the IROC of this function at this place when the tangent line is known to pass through 1, f of 1, and 3 minus 1. Okay, now I just need to think, what do I know about IROC? The instantaneous rate of change. That is the slope of the tangent line. Okay, and how do I find the slope of the tangent line? Well, I need to find 2 points that are on the tangent line. Okay, well, I know one of them. And this one, right, I can say, okay, how much is f of 1? So f of 1, if I substitute that in, right, that's negative, parentheses 1 squared plus 4 gives me a 3, right? 1 squared is 1, negative 1 plus 4, 3. Okay, so I have the point, so then I'm just going to go through and calculate. So find the slope between these 2 points. So this is 1 comma 3 as a point, and I have the other point there. So change in y, so 3 minus negative 1 over 1 minus 3. Okay, so let's see, that's 4 over negative 2, also known as negative 2. Okay, so then I can say this, and then if I wanted to, I could say the change, or I can say the IROC at x is equal to negative 1 is minus 2. And I could write it in a sentence. That's fine. Okay, I could also say negative 2 units for a 1 unit increase in x. There we go. Okay. Now, all of this, right, this is just kind of theoretical. How does this happen in reality? Okay, how do we work with this in a physical context? And so one context that you will see at some point in your life is average speed. So this is kind of akin to, you set your cruise control on 65, drive for 2 hours, and then, see where you're at. But average speed is calculated as change in distance over change in time. Okay. The only thing is when we look at a small time interval, i.e., like 0 second or like 0.0000 or 0.0001 second, okay, that is going to give us, instead of average, really instantaneous speed. So your speedometer in your car is actually measuring instantaneous speed rather than average speed because the time interval is effectively zero. Okay, so here we go. We are given a context where we're looking at rock on Mars. Okay, we're given some information, blah, blah, blah. We have a function. That's lovely. Using time intervals provided and average rates of change over those intervals, we want to estimate the instantaneous rate of change or instantaneous speed of the rock at 1 second. So here we go. We have average rate of change from 1 to 2 is that. From 1 to 1.5, so we're decreasing towards 1. 1 to 1.1, okay, fine. 1 to 1.001, okay. And so this pattern is kind of like that example we showed at the beginning. We're getting closer and closer to 1, and we just want to estimate how much is the instantaneous rate of change. Well, based on this progression of numbers, right, it's getting larger, right? So it's increasing, it's increasing, it's increasing, but it didn't change as much from when we changed it from 1.1 to 1.001. So maybe, I don't know, I'm going to say about, I don't know, 6.3 maybe. Okay. And so right now, algebraically, numerically, we don't have exact methods on how to find this. That comes with calculus. If you're given a context like this and you're asked to, say anything about the instantaneous rate of change or the instantaneous speed, right? I can maybe should say instantaneous speed here. And this would be in mile or meters per second. It would need to be an estimate. Okay, we cannot find these exactly. So if you're off a little bit, fine. Just don't give me something wildly different like, oh, it's 10 meters per second, right? Go based on the progression of numbers, and that should get you reasonably close.